So last lesson of the year, 107, Convergent Geometric Series, and some more with sigma notation. And just to blow you away a little bit, although I think I kind of hinted at this the other day, convergent just means that it can be infinite and it has a sum. We can keep adding forever and ever and ever and actually get one single number that is our correct answer. But it's only a special case, and it will only work if we are talking about geometric series. But before we get into the special case and how that works, I want us to review a little bit with sigma notation and how that works and how we can kind of go back and forth between the two. So if we start with that Greek letter that looks kind of like a sideways M or something, it is the uppercase letter sigma in the Greek alphabet, and it means sum. It means you're going to add up a whole bunch of terms. You are going to have a formula out here for the nth term, and then it's going to tell you what numbers to plug in. You can start anywhere you want. Most of the ones we do will start with 1 just to keep it simple. And then it tells you the last number that you're going to use for n. So if it has n equals 1 to 7, you're going to have 7 terms in there. If it has n equals 0 up to 8, you're actually going to have 9 terms in there because you're going to put 0 in, then you're going to put 1 in, 2 in, 3 in, and keep going until you've put 8 in. I could go from 100 to 200, anything I want on that. When we put up here the infinity symbol, that means we go forever, so plus dot, dot, dot on that. So just to practice a little bit with how this works, this one says we're going to start with 3 and go to 7. And I said, oh, let's use A instead of N for the variable. As long as the letter that they put here under the sigma matches the letter in the formula, we're fine. So this one says that we need to take 5 times 2 cubed plus 5 times 2 to the 4th plus 5 times 2 to the 5th plus 5 times 2 to the 6th plus 5 times 2 to the 7th. We started with 3 and we kept going until we got to 7. And so if we wanted to multiply those out, 8 times 5 is 40 plus 80 plus, whoops, not 120, 160 plus 320 plus 640. And if we added those all together, we would get 1,240 because it's finite, it's got a sum, we can add it up. What kind of series is that, by the way? And probably the easiest place for you to look might be right here, that second line that I wrote out. Levi? It is a geometric one. And it kind of fits our pattern for the nth term with a first term and then an r to a power, except this said don't start with 1. We started, so it's a little bit off because we started with a equals 3, but we're going to make ours match up to that formula just to keep it easier and simpler for us to come up with those. So let's take a look at this one, and let's see if we can indeed go the other way with this. So we have 4 terms, so I'm going to keep it simple. And since I have 4 terms, I'm going to say 1 up to 4. And then I'm going to look at that. Is that arithmetic or geometric? Now, what do you think? Do we multiply by the same thing over and over to get the next term, or do we add? So we're going to add, so it's going to be arithmetic. We know our formula for an arithmetic one is that the nth term is the first term plus n minus 1 times d. Do we know the first term of that series, Michelle? So I'm going to put in a 3 for my first term, plus, John, what's my common difference?
4.
So I'm going to put a 4 for the d and the n minus 1. So I'm just using the formula that I know for the type of series that is and plugging in the given numbers in there. Does it work? If n is 1, 3 plus 4 times 1 minus 1, 3 plus 0, that is 3. Then if we go to 2, 3 plus 4 times 2 minus 1 is 1, 3 plus 4 is 7. Then put a 3 in. 3 plus 4 times 2, that's 11, it worked. Then finally put the 4 in. 3 plus 4 times 3 is 15. Our formula worked. Okay, let's try another one here. So take a look at that. I want to see hands up. Everybody's going to vote. Do you think this one is arithmetic? How many think it's geometric? And by far, the geometrics are unanimous there, and you are correct. So for this one, I'm going to stick with n because I'm used to my formula being a sub n. I have 1, 2, 3, 4, 5, 6, 7 terms in there. So I need 7 terms to add up. Ryan, what is my formula for the nth term of a geometric series or sequence?
It is A1 times 1 minus R3n.
Times r to the n minus 1.
Oh, yeah. Then it's all over 1 minus R.
Oh, no, not the total of it. You're looking at the sum of it. I just want the term.
Oh, okay.
Because right now I'll worry about the sums of these later, but you're exactly right with that. So if it's just the terms to get this in sigma notation, we're going to have that. So everybody shout out, what's my first term? Do I need to write down 1 times r? I'll just let it be an invisible 1 over here in my formula. And now everybody shout out, what is r? So I'm going to put the 2 right there and the n minus 1. Does that work? When I plug in 1, do I get 2 to the 0 is 1? When I go up 1 and put in a 2, I have 2 to the 2 minus 1, 2 to the 3 minus 1, and so on. Now let's go to what Ryan was thinking I was asking there. Let's do the sum of this one with that formula. Since it's finite, we've got our formula for that. And that was the first term times 1 minus r to the n over 1 minus r. And let's see if we're going to get something that will make sense with this. So we'll put in, the first term was 1. 1 minus, you guys told me r was 2. We have 7 terms in there over 1 minus 2. I think I got that right. And let's see what in the world we can come up with for that. So denominator is going to be -1. Numerator is going to be 1 minus, let's see, 2 to the 5th is 32. 2 to the 6th is 64. So 128. So -127 over -1 is going to be +127. Who's got your calculator out real fast? Anybody already have one out then? Just do 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. Did we get that?
No, I have.
Okay, did we get that?
Yeah.
Okay, so Ben verified it for us on the calculator that that's right. Question, Etsia.
Okay, so on the first one, like, you know you can add 4, and on the second one, you know you can, like, multiply by 2.
Uh-huh.
So is that what determines, like, if it's geometric or...
Yes. Arithmetic is you add the same thing over and over. So you use all of your formulas for arithmetic terms, for arithmetic totals on the sum. If you multiply over and over, it's geometric. And then you use your geometric formula for the nth term, or for the sum of the first n, or what we'll get today for the infinite sum for some of those. Any other questions? Okay, really short one right here. It would be really, really easy for us just to say we have what, negative 10 plus 45, that equals 35. But what I want to do is to write it in sigma notation. So let's see if we can do that. How many terms, everybody? Is this one arithmetic or geometric, Lily Rose? And what's the common ratio? -3. So now I need to put in my a1 r to the n minus 1 for my terms to get this to sigma notation. First term was 5. And then you said that the common ratio was -3. So I'm going to have a -3 right here to the n minus 1. And there's that one in sigma notation. Okay, now we're going to get to one that's really going to be a basis for what we're going to be doing today. Arithmetic or geometric, Graham?
Geometric.
I mean that fellow, can't see that one. So geometric. And Isaac, what's the ratio? Okay, and let's see. Ava, you've got your calculator out. Just add up a half plus a fourth plus an eighth plus a 16th plus a 32nd for me. And leave it in fraction form. Don't change it to a decimal. And let's just see what we get for that. And we'll also write this in sigma notation. So we'll work on that while I've got Ava and looks like 1 or 2 others checking what that's going to add up to for us. How many terms do I need? Micah, how many terms do I have?
5.
So I need n going from 1 to 5. It's geometric, so that means my nth term is a1 r to the n minus 1. a1 is a half. R is a half to the n minus 1. Since it's just a coincidence that a1 and r are the same, I've got a half to the first times a half to another power. I'm going to clean that up just a little bit and add the exponents together. So 1 plus n minus 1 means that I am looking at a half to the n. Okay, what do we get for that total, Ava? So we got that is 31 over 32 by just adding them up on our calculator. If we wanted to use the formula from the other day, we could say that the sum of the first 5, this is geometric, so I need the geometric formula, a1 times 1 minus r to the 5th over 1 minus r. So I would need, it's going to look messy, a half times 1 minus, a half to the 5th would be 1 minus a 32nd, over 1 minus a half. Does that look about right? Because I haven't done this on my notes page, so keep me honest here. All right, so denominator is going to be a half, right? Can I go ahead and just cancel the half with the half? And 1 minus a 32nd is going to be 31 32nds. Now what I want to propose for today I'll take that very same series that I'm looking at, but I won't stop. I'll let it go to infinity. So I am looking at a half plus a fourth plus an eighth forever and ever. And I'm going to say that does actually have a sum that we can find. It is a very special kind of geometric series. If I tried to do that with this one, no sum. It just keeps changing forever and ever and ever. But this last one is a special case, and I'll talk about what kind of special case here in a little bit. To figure out what that sum needs to add up to, just going to jump down to this one. We are going to figure that out by thinking about a square. And let's suppose that each side of that big original square is 1. So the area of the big square has to be side times side, 1 times 1 is just going to be 1. Now, if I added up all of the little squares and rectangles inside of it, it would have to add up to 1. So if I also took the sum of all the squares, rectangles inside, that would have to give me the whole big square, which would be 1. Now, the way that I created this and the way I'm going to add them up, I'm going to keep dividing it forever and ever, even though my picture I stacked on it. I am going to take this half of the square plus this fourth of the original square plus this eighth of the original square plus this 16th of the original square plus this 1/32 plus then 1/64. And then these are going to keep dividing over and over and over, so small that I can't even draw them anymore. So if I took a half plus a fourth plus an eighth plus a 16th plus a 32nd forever and ever, yes, it would need to have a sum, and it would need to equal 1. So you believe me on the geometric model. What is special about this one is R is a half. And this one up here, if I took 3 plus 6 plus 12 plus 24 plus 48, would I ever be able to stop adding? My numbers get bigger and bigger, so no, this one does not have a sum. This other one up here was arithmetic. 3 plus 7 plus 11 plus 15 plus 19. I'm adding bigger and bigger numbers. Is it going to ever have a sum? No, this one will not. What's special here is the things that I was adding kept getting smaller and smaller and smaller. They kept getting closer and closer to 0. That is only going to happen if it's geometric and if we have an R, either positive or negative, that is a fraction, so that the absolute value is less than 1. This is our special case for it to be convergent. Geometric series, absolute value of R needs to be less than 1 in order for it to converge, for us to be able to get a sum. And that's what I've got right here. Absolute value of R is less than 1. So the terms are getting closer and closer to 0. It's convergent. Divergent would be absolute value of R is greater than or equal to 1. We either add the same thing over and over and over and over, or we add bigger and bigger and bigger things each time. Sure would be nice to have a formula, because I don't think I can deal with those pictures every single time that I'm trying to add up a geometric series. I don't think I can deal with the square that I'm dividing over and over and like that to figure out what it's going to have to be. So let's see if we can come up with a formula. So if we had geometric, we've already been reviewing that our formula is 1 minus r to the n over 1 minus r. Now I want the infinite sum. So I want n to keep going forever and ever. So I'm going to do something with this one that is a little bit of an introduction to something you will do quite a bit of next year. So if the absolute value of r is less than 1, that means r to the n gets closer and closer to 0, right? So we're going to call that the limit as n goes to infinity of r to the n is 0. So to get my infinite sum, where I'm going from 1 to infinity, I need to take the limit as n goes on forever and ever of a1 over 1 minus r to the n over 1 minus r. Well, no matter how far I go, the first term is always the first term, so a1 stays a1. 1 minus, the r's are going to get closer and because the r is a fraction. When we take it to powers, it's going to get closer and closer to 0. So this one is like a 1 minus 0 right there over 1 minus r. So this is just a 1 times a1. So the infinite sum is just a1 over 1 minus r. And if we did that for our fraction series that we were talking about, if we did that for our half plus a fourth plus an eighth that we just did with the square that we divided into different squares and rectangles, that would become a half for the first term over 1 minus a half for the common ratio, a half over a half is 1, and that's what we thought from our geometric model on that. So formula for you to memorize, last formula of the year, if it is convergent, which means the absolute value of r is less than 1. It's between -1 and +1. And it is geometric. So, write in sigma notation and find the sum. So here's sigma notation. I'm going to let n go from 1 to infinity. Geometric or arithmetic? Everybody shout out. Which is it? It is geometric. So first term is 5. What is my r? It is a half. Is that between -1/2 or -1 and 1? So it is going to be convergent. So my formula is a1 r to the n minus 1. To get my sum, it needs to be a1 over 1 minus r. So it needs to be 5 over 1 minus a half. 5 over a half is 10. See how easy that one was? Okay, next example. I'm going to do 2 ways. What is the total? It will fall. And what is the total distance it travels? So falls, that's going to be the downhill part, or the downward part. So it's going to go down 12, and then it is going to bounce up 12 times 2/5. Okay, that bounce I don't want to include in part A. I do want to include this next downward one, which is the very same thing. Then it's going to bounce up, and I don't want to count that. but it is 12 times 2/5 squared. And then it's going to fall that same distance, so I do want to count that. And so on and so on and so on. So if I want part A, just the falls, is it geometric? 12 plus 12 times 2/5 plus 12 times 2/5 squared. Does that geometric mean? So I need, is it convergent? What's my common ratio? Matthias? Is that between -1 and +1? So it's convergent. So just for my falls, it's going to be the first term over 1 minus r. It's going to keep bouncing forever and ever, even though it looks to me like it stops at some point. It's going to go forever. So just for the falls, it's going to be 12 over 1 minus 2/5. And I'm going to do multiply numerator denominator by dinky denominator and get that that has to be 60 over 5 minus 2, so over 3. So my falls need to be 20 feet for part A. Everybody good with that? Okay, now for the total. That's going to be the drops and the bounces, right? So that is going to be 20 plus the bounces. Now there are two ways that I can get the sum of all of those bounces, so help me out here. Who can tell me one way that I can get them? If I want just the parts I drew in black, come on, you've done some of these. Luca, what do you think? How can we get just the parts in black? Okay, good thinking. You're on to the easy way. And because I want to do it both ways. So one way you could do it is to say, oh, just for the bounces, the first bounce is 12 times 2/5 over 1 minus 2/5. It has a different first term if we are plugging into the formula for the infinite sum. And so the hard way would be to take 20 plus whatever that is. And that one is such a mess. Let me multiply by dinky denominator over dinky denominator, so I'll multiply both by 5. So that means that becomes 24 in the numerator, 5 minus 2 in the denominator, so 3, so that I have 20 plus 8 for 28 feet total. And that's the harder way because of this mess to evaluate. But I love that Luca observed the shorter, easier way is the downs and the bounces up all match up except for the very first drop. So the drops have this extra 12 in there to begin with. So if I took away that 12 from this first total, that would tell me all of these other bounces that I'm looking at. So the shorter, easier way would have been 20 plus 20 minus 12, which was that first drop. So 20 plus 8 would have also given us our 28 feet. Everybody okay there? Okay, one more that we'll do together, and then a couple I'm going to have you guys try just for the practice. So we've got a dog that never, ever, ever gets tired and never wants to take a break and runs forever and ever without stopping to sleep. 8 miles the first hour, 3 miles the second hour, 9/8 miles the third hour, forever and ever and ever. And they want us to get a total. We can only do it if it is a convergent geometric series. what do you think? Is this geometric? This one's a little harder for me just to look at it and say yes or no. So Josh, you've been nodding your head. How can I figure out what the ratio is to check?
Oh, I just looked it up before. Oh, wait, you can include, if you do 82, so it's like 3 equals 8 times R squared.
It'd actually be R to the first because it's 1 minus. Easier way is to take one term and divide it by the term before it to see what we multiply by. I could take A6 over A5, A12 over A11. I could have done A3 over A2, but A1 and A2 have no fractions. So I'm going to say 3 over 8, maybe. So 8 times 3/8 is 3. It worked there. 3 times 3/8, does that give me 9/8? So yes, I am convinced that it is geometric with R being 3/8. Is 3/8 between -1 and 1? So yes, it is convergent. That means that our sum needs to be first term over 1 minus R, so 8 over 1 minus 3/8. And that would be, oh, instead of dinky denominators, I'll do it this way, A over 5/8. So that is flip and multiply 64 fifths, or 12 and 4/5, 12.8 miles. Questions from anyone on that? All right, I want you guys to try these last two. So I'll give you guys some time for each one and then we'll check. So on your own papers, I would like for you to find the sum of this. If it exists, verify that, it is going to converge, and then figure out what we will get there. The three of you at home, just type your answer into chat when you've finished it, and we'll check with everybody. All right, so you did a good job with that one, with a common ratio of 1/5 that it converged. Plug into the formula, and we got 5/2 for the sum. So let's do one last one for today's lesson. And this one, be a little bit careful on. There's a little bit different twist to this one. And we did not do an example that had this little bit of a twist to it. So just be careful as you think about this one. That with everybody. So everybody in class and at home is saying that you are getting a sum of 9 for this, which is correct. For this one, what was your common ratio? -1/3. We haven't had a negative ratio before. That was the little twist I was talking about. So that absolute value is less than 1, so it is still convergent. That means that our sum will be first term over 1 minus R, so 12 over 1 minus -1/3 becomes 1 plus 1/3. So we are looking at 12 over 4/3, which does indeed become 36 over 4, or 9 for that sum. So let's do this one in our sigma notation. We're going to go to infinity this time. And Gabe, what are we going to put in our formula there? Since it's geometric, we know we need it to be A1 R to the n minus 1.
12.
Thumbs up, thumbs down. What do you guys think there? See a lot of thumbs up in the classroom. Let's go back and let's do number 1, also in sigma notation. So n would go from 1 to infinity. What was our first term, everybody? 2. What was our ratio there? And then that would be to the n minus 1. All right, questions? All right, good job. That wraps up our new content for this entire school year. You'll finish the rest of the green book next year.